So now let's take a look at how you would do it with Ampere's law. So with Ampere's law, you can draw a contour, just any contour that encloses the current, and then it'll work, right? So let's choose a contour that works best for us. So I'm going to propose just a loop, a circle in this direction, and the radius is going to be rho. So for every rho that depending on where my observer is, I'm just going to use that as my radius and loop around, and that will be my closed contour. So I'm going to choose circle, closed contour, radius rho, and we're going to go from 0 to 2 pi. In this case, what's our DL? What's our little length segment? That's the other tricky question. So the length segment is in the phi direction, right? So I just say d phi, and then I move on, right? No, don't forget, it's not a length segment until you multiply it by the radius, right? Otherwise, this is in units of angles, so radians. So you multiply that by the radius, now you have a proper length angle. So this is your DL, and what direction would the field be? So if you use your right-hand rule, the field would be in the phi direction, right? So if you use the right-hand rule, the current, let's see, right-hand rule, if you apply the right-hand rule, you'll see the current is in the z direction, and your source observer vector is in the rho direction. Therefore, your field is going to be in the phi direction. Or another way to view it is if this conforms to the right-hand rule, the current is going to be in the direction of your ds vector, which is defined using the right-hand rule. So you curl your hands around, your thumb's pointing in the positive z direction, and that's going to along the direction of the current. Therefore, since your ds, if you define it this way, is in the direction of the current, the field is going to be in the phi direction. Okay, now recall when we were doing Gauss's law and we said that when you're doing the integral form, I'll just write epsilon e instead, you had to have symmetry, right? One of the key criteria for the integral form to be a way for you to solve for the E field everywhere is that E has to be independent of the variables in ds that you're integrating against so that you could pull it out. Otherwise, it's not going to work. In our case, we can see that there's symmetry in the phi direction, because if I'm standing over here versus if I'm standing over here, everything looks the same, right? In my sheltered universe example. It's also symmetric in z, or independent of z, because if I move this whole thing upwards or downwards by some amount, everything's going to look the same to me. So you expect it to only vary by rho. But aside from the point, you don't have to worry about that for now. The main thing is that h phi does not depend on phi, which means that this integral is going to work out. So once you've done all that thinking through and all that groundwork, you're basically there. You've already won. You just have to write through the rest of the problem, and it's in its last gasp effort to thwart you. You basically have it down now. Let's just write out what h.dl is. So in this case, we can say that h is only going to have a phi component, phi hat. So we said that, we used our right-hand rule and intuited that it's going to be in the phi hat direction, so it'll only have a phi component. And then we're going to take the dot product with our dl, which we have previously found to be rho d phi in the phi direction. And then we're doing a closed integral, so we're going to integrate this from 0 to 2 pi. Right? And that's going to be equal to the I enclosed, which is just going to be the current here. Right, so next up, we just take the dot product, and we're left with h phi rho d phi from 0 to 2 pi is going to be equal to I. And look, none of these depend on phi, so we can pull them out, and we're left with h phi rho integral from 0 to 2 pi of d phi is going to be equal to I. This whole thing is equal to 2 pi. So therefore, you get 2 pi rho h phi is going to be equal to I. H phi is therefore equal to I over 2 pi rho. So then we end up with the same result. H has a single component, that's the phi component. I over 2 pi rho in the phi direction. So happily, you see that you can use the Biot-Savart law or Ampere's circuit law to arrive at the magnetic field. In both cases, the hardest part probably is the setup and identifying the symmetries. In this case, writing out the source observer vector, taking the cross product. In the case of this problem also with the Biot-Savart law, you have this ugly integral that you have to use either a lookup table, an integral table, or a computer to figure out. But once you plug it in, it actually has a pretty nice solution that you plug in. But in the case of Ampere's circuit law, once you identify the symmetry and point out the components, you have a dot product, which is much happier than a cross product. But either way, we're fearless, right? We don't worry about it either way. We just solve it. So, but again, recognizing the symmetry needed, making sure that h phi does not depend on phi, so we can pull it out. And then you just set up the integral, pull out all the constants, integrate whatever simple thing is left in there, and shove all the non-h components to the right-hand side, and you win.